Welcome to The Explainer. Today, we're diving into the incredible breakthroughs that are turning quantum computers from, this mind-bending, almost sci-fi theory into a real, scalable technology. So yeah, let's dive in.
So, our story really kicks off with an idea so strange that it genuinely freaked out Albert Einstein. He famously called it spooky action at a distance. And what he was talking about is one of the weirdest but also most powerful ideas in all of physics: quantum entanglement.
So what on earth is it? Well, imagine you have two particles that are linked in this very special way. If you check on one of them, you instantly know the state of the other one, even if it's on the other side of the universe. It's this instant, spooky connection that is the real engine behind a quantum computer's incredible power.
But here's the thing. This isn't just a thought experiment for physicists scribbling on a blackboard anymore. No way. Scientists are now taking this spooky action and they are building it literally onto microchips.
And this, right here, just shows you the giant leap we're taking. What you're looking at is a silicon photonic chip. It's a tiny piece of hardware engineered to create and control entangled particles of light. We're officially moving from abstract physics to real hardware that you can actually hold. Now, to really wrap your head around the potential here, just think about this. A quantum computer with just 300 perfectly entangled quantum bits, we call them qubits, could, in theory, hold and process more bits of information than there are atoms in the entire known universe. I mean, just let that sink in for a second. That is the kind of game-changing power we're talking about. Okay, so if the potential is that massive, why don't we all have quantum laptops sitting on our desks right now? Well, as you can probably guess, trying to wrangle this spooky power comes with some pretty major challenges. Let's take a look at the big ones.
So here's the deal. These quantum bits, or qubits, are kind of the heroes and the villains of the story. They're the building blocks, and they're incredibly powerful, but they are also unbelievably fragile. I mean, the slightest little thing, a tiny vibration, a stray bit of heat, any kind of environmental noise can make them lose their quantum state and mess up the whole calculation. And on top of that, trying to connect a whole bunch of them together, historically, that's been a monster of a problem. But this is where the story gets really, really exciting. In just the last year or so, researchers have landed some major punches against these quantum villains. They're starting to solve problems that, frankly, a lot of people thought might be insurmountable.
Okay, first up, that error problem. In a huge experiment, a team at Harvard actually built what's called a fault-tolerant quantum system. Using 448 qubits, their machine can literally find and fix its own mistakes while it's running. Think of it like a computer that can proofread its own work on the fly. This is a massive step towards building quantum computers that are actually reliable. Then over at Durham University, scientists did something else that's never been done before. They managed to entangle entire molecules. Now, why is that a big deal? Well, molecules have more tricks up their sleeve than single atoms do. They can vibrate, they can rotate. Being able to use those extra properties could unlock way more advanced quantum computers and sensors down the line.
And get this, at the Technion in Israel, researchers found something totally new, a whole different type of entanglement. By using this property called total angular momentum, they found a new recipe that could let us shrink quantum components down, making them much more compact.
So these are all just amazing advances happening in labs around the world. But they all point towards the single biggest question that has really haunted this entire field for decades.
How do you go from these incredible but really delicate lab experiments to a technology you can mass produce? How do you build a processor that has not just a few hundred qubits, but millions or even billions of them, just like the chip in your phone?
The answer, it turns out, has been hiding in plain sight this whole time. It's the same material that our entire digital world is built on: silicon.
So why silicon? Well, think about it. The semiconductor industry has spent the last 50 years and trillions of dollars getting ridiculously good at building unbelievably complex things out of silicon. All of that knowledge, all those factories, they can be adapted to build quantum computers. We're talking about building quantum devices at the same tiny 20-nanometer scale as the transistors in the phone you're probably holding right now. Researchers at the University of New South Wales came up with this just perfect analogy to explain their breakthrough. They figured out how to connect two atomic nuclei that were far apart inside a silicon chip, which was, for a long time, a huge roadblock for scaling up. Let's break that down, because it's really the key. The old way, well, it was like trying to have a conversation in one tiny soundproof room. All the atomic nuclei had to be huddled right next to each other.
It worked, sure, but you couldn't fit very many in there. But this new way is like giving everyone in different quiet rooms their own telephone. The electrons act like the phone line, letting distant nuclei talk to each other. It's a system that is fundamentally designed to be scaled up.
So let's put all the pieces together. We've got breakthroughs in fixing errors, we've got new ways to entangle particles, and now we have a clear path to actually manufacturing this stuff using silicon. So what does this quantum future actually look like? I mean, the applications are truly going to change everything. We're talking about designing new life-saving drugs molecule by molecule, creating new materials we can't even imagine today, building communication networks that are literally unhackable. This will revolutionize AI, finance, and probably even our basic understanding of the universe itself. So we've officially gone from spooky action to scalable action. Thanks to silicon, the whole conversation has changed. It's not really about if we can build large, useful quantum computers anymore. The question now is, what should we do with them first? The quantum age is here, and it's being built on the very same foundation as our digital one. The only real question left is, what do we build?